You are welcome to GMAETS 41's lesson. Today we are going to look at the topic nitriles in organic chemistry. What is the functional group of nitrile? Nitriles generally are identified by the functional group RCN, where R represents the alkyl group. Then the CN is the cyanide group. The functional group is written like this: RC triple bonded to nitrogen. Of course, we expect this triple bond to nitrogen. Yes, it's expected because you know that the valency of nitrogen is 3. That is the combining power of nitrogen. Okay, if you check back in your inorganic chemistry, you remember that nitrogen needs 3 electrons to complete its outermost shell. And of course, that's why we are saying something like this. Now, what is the general pattern of naming these homolog nitriles? Nitriles generally are named corresponding to its alkanoic acid derivative. The only difference is that the oic group in alkanoic acid is now replaced with onitrile. It's replaced with onitrile. Okay? So that maybe if you have something like ethanoic acid, in nitriles, you'll be having ethanonitrile. If you have propanoic acid, in nitriles, you'll be having propanonitrile. And of course, we don't want to forget, please, the cyanide group can also be named in line with the alkyl cyanide, okay? So the nitrile groups can be named in accordance with the cyanide group, where in that case, we'll be having alkyl cyanide. The reason why this is possible is because of this CN part. Remember that CN represents the cyanide group. So one can still choose to name, of course, in simpler cases anyway, the nitrite group, one can still choose to name them in accordance to alkyl cyanide. Let us look at some examples of members of the nitrile homolog. Okay, we have this one, CH3CN. As a nitrite group, the name of this compound is ethanonitrile. Why? 2 carbon atoms in the homolog series correspond to ethane, okay, ethane, E-T-H-A-N. Okay, as a nitrite group, it becomes onitrile. So we have ethanonitrile. Of course, if we want to call this as a cyanide, it would be methyl cyanide. Okay, knowing that CH3 is a methyl attachment on the cyanide group. So we can call this ethanonitrile following the alkanonitrile naming, or we can call it the methyl cyanide following the alkyl cyanide naming. Okay, but in this lesson and video, we are going to use the alkanonitrile naming. Then this is propanonitrile. You can see we have 3 carbons here, giving us propanonitrile. Now we are going to look at how the nitrile groups are being prepared, and of course, their chemical properties. We now want to look at how we can prepare the nitrile groups. There are 2 methods we're going to talk about here. Okay, in one of the methods, we obtain the nitrile groups from haloalkane. Take note, the compound from where we can get the nitrile group from. That is haloalkane. In the second method, we get the nitrile groups from the acid amide. Acid amide is one derivative of alkanoic acid. When you want to obtain the nitriles from haloalkane, what do? Usually you react the haloalkane with sodium cyanide. You heat the haloalkane with sodium cyanide in methanolic or ethanolic solution. During the reaction, what really happens is the removal of the halogen, usually bromine or chlorine, from the haloalkane by the cyanide ion. You can look at the general scheme for the reaction. This RBR, this R represents alkyl, this BR is bromine, so this is bromoalkane, alright, it's a haloalkane. Reacted with the cyanide group, this usually like sodium cyanide, in the presence of a solution of methanol or ethanol. During the reaction, we have the cyanide group being introduced into the alkyl, so you have RC triple bonded to nitrogen. The bromine will be displaced, that is removed and replaced by the cyanide group. Now, instead of using methanolic or ethanolic solution, we can use DMSO, that is dimethyl sulfoxide, or we can also use DMF, that is dimethyl formamide, as the solution in which we hit the halogen with the sodium cyanide. Now, in the second method, the reaction is known as dehydration. Remember, in the first method, the reaction is displacement. This next one, from acid amide, is known as dehydration reaction. And generally, we know that dehydration reaction is the removal of water molecule from a compound or a substance. Okay, now we have the general scheme for the reaction here. This is the functional group of the acid amide, that is RCONH2. This CONH2 represents the acid amide functional group. Now, when you dehydrate them, what do? You're removing water molecule from the compound. So this oxygen will react with this hydrogen to give you water, and it will be eliminated. Of course, if this is eliminated, you'll be left with CN. And don't forget, the triple bond will be introduced here as usual, as we know, because the CONH part is generally written like this. Okay? So that when this H2 picks this oxygen to give you water, which is eliminated, removed, this bond will now link up with the two other bonds that will give you the triple bond, which links up the nitrogen to give us the nitrile group. So this is how the reaction takes place, the general scheme. When eliminating water from the acid amide, we can use phosphorus 5 oxide as the solvent. We can also choose to react the acid amide directly with thionyl chloride. Thionyl chloride. Thionyl chloride is SOCl2. That's thionyl chloride. Now we are going to look at reactions that would explain the scheme that have been mentioned here. That's the next thing we're going to talk about. We have 1A and 1B for the displacement of halogens from halogenoalkane using a cyanide ion. The 1A and 1B are similar reactions. The only difference is the solvent, the solution we use during the reaction, okay? Now, in the first case, when we are hitting the halogenoalkane with sodium cyanide, is that okay? When we are hitting the halogenoalkane with sodium cyanide, we may choose to use ethanolic or methanolic solution. Then in the 1B, instead of using methanolic or ethanolic solution, we may choose to use an aprotic solvent. Aprotic solvent. One of the aprotic solvent is DMSO, that is dimethyl sulfur oxide, or DMF, which is dimethyl formamide. An aprotic solvent is one that cannot be able to give out hydrogen ion. That is, it cannot transfer a proton during chemical reaction. Now let us look at what happens. This is a halogenoalkane. If you count the number of carbons here, you have 1, 2, 3, 4, 5, 6. You know, there are 4 carbons here. You can see 4 atoms. Added to this, making it 5. Added to this, making it what? 6. The name of this compound is bromohexane. Bromohexane. If you expand it, you will see yourself. So during the chemical reaction, this is the carbon of the functional group. Look at it. So this is where this solvent is going to attack. So before the attack, there's going to be a bond cleavage. That is bond breaking. This sodium cyanide will break at this point. Then the halogenoalkane will break at this point. Now the cyanide group is negative, and then sodium here is positive ion. During the breaking here, bromine will be negative, this carbon will be positive, giving us what we call carbocation. There will now be an interchange of ions, of course following the laws of attraction, positive to negative, negative to positive, okay? So this sodium is going to pick this bromine to give us sodium bromide, which is the leaving group. Then watch what happens. This cyanide group will attach to this carbon to give us CH2CN. Look at it. Now, did you notice that there is an introduction of one carbon atom into the original halogenoalkane that is used for the preparation here? And what does that tell us? Whenever you're preparing nitriles from halogenoalkane, The nitride that is obtained is always one carbon atom greater than the haloalkane from where it is obtained from. And that is why, like here, we have 6 carbons in the haloalkane. If you count the carbons here, you will see that there are 7, an increase in 1. This is 4 carbon atoms here in the bracket, added to this 5, added to this 6, added to this 7. The name of this compound is heptanonitride. It's the same thing that happens in 1B reaction. The only difference is that you use an aprotic solvent, which has been explained already, okay, dimethyl sulfur oxide or dimethyl formamide, to carry out the reaction. You still get the same product, which means there will be a bond cleavage here. You see, in this case, if you count the number of carbon atoms here, you have 1. Here there is 2. Add the 2 here is 3. Added to this carbon, you have 4, which means this is chlorobutane. Chloro what? Butane. Okay, now during the reaction, after the bond breakage, where they are supposed to break, as shown here already, there will be a ionic interchange. A displacement reaction will happen. Chlorine will be removed and replaced by the cyanide. That's what we call it, displacement. Displacement reaction is simply removal of something and replacement of that thing by another. And that gives us this. Once again, notice that as this CN, cyanide functional group, enters this haloalkane, from when you remove this chlorine, there will be an increase in carbon. This becomes CH2CN. Look at it here. Okay? Look at it here. And there is an increase in carbon atom in the nitride group that is found. From here, if you count the number of carbon atoms, this is 1, 2, 3, 4, and 5. So this is pentanonitride. Pentanonitride obtained from chlorobutane. I believe this is making sense. Now let us proceed to the second method of preparation of nitriles, which has to do with dehydration of acid amides. You can dehydrate the acid amide using phosphorus 5 oxide. You can also choose to react the acid amide with thionyl chloride. And we have it here. This is the first reaction. These are phosphorus 5 oxide. This compound is the acid amide. If we name this compound, you can see that this CH3 is in bracket. There are 2 of them attached to this. Okay? And then we have 1, 2, 3. Which means that the name of this compound, of course, is going to be 2-methyl-propanamide. If you expand this, the name of the compound will be 2-methyl-propanamide. Now, during the chemical reaction, remember that you're trying to remove what? Water molecule. So what's going to happen? There will be an extraction of this oxygen together with this hydrogen. They will react to give you water, which is the living group. Once this oxygen and H2 goes off, you notice that here you'll be left with Cn. Once again, you see what you were told before, that the chemical reaction of organic compounds usually centers on the carbon of the functional group. And in acid amide, the carbon of the functional group is the CONH2. So all the attack focuses at that point. That's going to give us CH3 in bracket 2, then CHCN. You see that carbon and nitrogen will just be the only thing left here. And one can name this compound, of course. There is an attachment there. If you expand this compound, what are you going to get? Please watch. This CH3 is an attachment here. That's why it is in brackets. So we're going to have CHCN here. Then this CH3, there are 2 of them. Let's put it this way, CH3, CH3. If you notice these and you count, just like we treated in the nomenclature, this is 1, 2, and 3. In the second carbon atom, there is methyl attachment. So the name of this compound is 2-methyl-propanonitride. So that's how we got this. Do not forget, in the dehydration reaction, oxygen and hydrogen is being removed by the phosphorus 5 oxide. What of the case 2B here, where you react the acid amide with thionyl chloride? What's going to happen with this thionyl chloride? During the reaction, there will be a bond cleavage. Let's watch what's going to happen. In the thionyl chloride, there will be a bond breaking between the SO and the Cl2. Then we come to this. This oxygen will be extracted as usual. This hydrogen will also be extracted. When they're being extracted, what's going to happen? This oxygen will react with this SO to give us SO2, that is sulfur oxide, the living group, a gas. This hydrogen, 2 atoms of it will react with this chlorine, 2 atoms to give us 2 moles of hydrogen chloride, the living group. So what is left? You will see that we'll be left with CH3, CH2 in bracket 4. This is not an attachment. This is not CH3, it's CH2, so it's a continuation of the chain. Then Cn will be left, which is what we have here. And of course, if we try to name these nitride groups, let's look at it. 1 carbon added to 4 carbons, that is 5. Added to this 1 carbon, that is 6. Therefore, this is hexanonitrile. You notice that in this second phase of the reaction, that is dehydration of amide, the same number of carbon atom you use from the amide group, it is the same number of carbon atom you would have in the nitride that is being formed. And this is simply the chemical explanation to the methods of preparing nitriles. In this video now, we want to talk about the chemical properties of nitriles. Before we move into that, we want to quickly highlight some of the physical properties that are necessary for you to know. For example, the lower members of nitriles are liquid, they have pleasant smell, they are colorless, and of course they are water soluble, that is, they are soluble in water. Also, the boiling point of nitriles is rather very high. If you compare with the alkanes, you'll see disparity, a lot of differences in terms of the boiling point. For example, butane and propanonitrile. Butane is an alkane. Propanonitrile is a nitrile. Their molecular masses is relatively close. But now, butane boils at minus 0.5 degrees centigrade, while propanonitrile boils at 97 degrees centigrade. You can see the difference very far. Now, what is responsible for the high boiling point of nitriles as compared to corresponding homoalogs? Look at nitrile is represented by this functional group. Okay, this part of nitrile is polar. The functional group part of nitrile is what? Polar. Because it is polar, it makes the boiling point very high. Nitrogen here has a partial negative polarity, while carbon here has a partial positive polarity. And it is the polar nature of the functional group side of nitriles that makes the boiling point quite very high. Now I want to talk about the chemical properties. We have 2 chemical properties we want to consider here. 1, hydrolysis. Hydrolysis is the reaction of a compound with water, or the introduction of water into a compound. Then 2, we talk about reduction reaction. Now look at the general scheme of the chemical properties, hydrolysis and reduction. When nitriles undergo hydrolysis, first of all, they produce an intermediate compound, that is acid amide. You can see that. Then further hydrolysis will now give alkanoic acid. So in general, when nitriles undergo acid hydrolysis, we expect that they're going to get the corresponding alkanoic acid. Yes, corresponding alkanoic acid, which means if you hydrolyze maybe ethanonitrile, you're expecting to get ethanoic acid. If you hydrolyze maybe butanonitrile, you expect to get butanoic acid. Of course, during the reaction, ammonia will be given off as a gas. Then we have reduction reaction. Generally, in reduction reaction, we convert nitriles to primary amines. This is a primary amine compound, okay? Now, what happened during the reaction? In the reduction reaction, we can either use catalytic hydrogenation process, or we can use a reducing agent like sodium in ethanol, okay? Sodium in ethanol. Or of course, we can use a compound called lithium tetrahydroaluminate 3. Lithium tetrahydroaluminate 3 is LiAl, then H4, okay? Li is lithium, then tetrahydroaluminate 4 hydrogen aluminate 3. So any of these reducing agent can be used. Remember, catalytic hydrogenation. In the catalytic hydrogenation, one uses a catalyst like platinum, palladium, or uranyl nickel when you are introducing hydrogen gas to the nitrile. Then you can use another reducing agent of your choice, sodium in ethanol, and then We'll talk about lithium tetrahydride aluminate. So this is the general scheme given here in the reaction. For this reaction here, the water during hydrolysis, the first part is going to break this triple bond into double bond, giving us this acid amide. Then further hydrolysis, this water molecule will break this bond here so as to free the NH2, and on freeing the NH2, hydrogen from here would react with the NH2 to give you the leaving group ammonia. Then the OH left in the water will now react with RCO, OH, giving the alkanoic acid. Now in this case, the 4 hydrogen atom that is of course supplied by the reducing agent, that is in reduction reaction, the 4 hydrogen atom will break this triple bond into 3 single bonds. Okay, we are going to use these chemical reactions to explain these schemes here. So here we go. Look at some examples of the chemical reaction showing hydrolysis and reduction reaction. We look at the first chemical reaction here. This is hydrolysis, the addition of water molecule to a nitride. This nitride is propanonitride. During the chemical reaction, what happens? Remember, the first step of the reaction produces what? Acid amide. This is propanamide. How does the reaction take place? Please, let's watch as we explain the scheme that I've been given. Now, this water will split into OH and H. That's hydroxide ion and hydrogen ion. Okay? So split into this. Then these are 2 atoms. These 2 atoms will attack the carbon of the functional group, that is the cyanide. The cyanide is something like this. Usually 2 atoms break a double bond into a single bond. So these 2 atoms will attack, breaking one of these bond here. So what's going to happen in the process? One of these bonds will be broken to a single bond. Okay, so we could have something like this. Then what is going to happen? This nitrogen will extract hydrogen and this hydrogen from here. So this nitrogen will extract this hydrogen and extract this hydrogen. Once it extracts this hydrogen, we are going to get NH2. Look at it, NH2. And that extraction will take place such that one of this oxygen will be left. That one oxygen will now bond to the double bond that is left. Remember that we had triple bond here first. The triple bond is broken into a double bond and a single bond. Look at it. Now nitrogen picks this hydrogen and this hydrogen to give us NH2 attached to this single bond. Then this oxygen will now be attached to the double bond. So you see, you're going to have C double bonded to oxygen and then NH2. Look at it here. So you notice that during the reaction, CH2 remains the same here, unaffected, because they are not the carbon of the functional group. Why this Cn, having undergone the attack here, gives us CONH2, and this is propanonitride. Sorry, this is propanamide, as I mentioned already. Now, if we further hydrolyze this propanamide, what is going to happen? Something similar again. Remember, the further hydrolysis of this is going to give us alkanoic acid. During the reaction, what happens? Watch. This water molecule will split again into the hydroxide ion and hydrogen ion. Then, this CONH2, remember this is the carbon of the functional group. There will be a bond cleavage here, so the bond will break there. This NH2 will react with this hydrogen to give us NH3 ammonia, which is going to leave. Then this OH will now be attracted to this oxygen to give us COOH. COOH. And this is the alkanoic acid obtained at the end of the reaction. The name of this alkanoic acid is propanoic acid. So you see, hydrolyzing propanonitride gives us what? Propanoic acid, but via propanamide. Let's actually go through propanamide first. Then we look at the explanation of reduction reaction. What happens? Let's look at it again. This 4 hydrogen atom is donated by the reducing agent. Here we are using the reducing agent sodium in ethanol. You can use catalytic hydrogenation, where you introduce hydrogen gas in the presence of a catalyst, either platinum or palladium or rhodium nickel. You can also choose to use lithium tetrahydroaluminate 3 as a reducing agent. I have decided to use this, okay? So let us see what's going to happen. During the reaction, this reducing agent supplies this 4 hydrogen. Remember, we said that 2 atoms break one double bond. Is that not so? That is one unsaturated bond rather. It means that 4 atoms will break 2 unsaturated bonds. So let us see how that applies here. Remember that in this case, Cn is the same as C triple bond N. So these 4 atoms, 2 of it will break one of these bonds, making it what? Single bond. You could have something like this. Then the remaining 2 hydrogen again will break the double bond here. Will break this double bond here, giving us what? Single bonds. So we'll have something of this kind. Now what's going to happen? There will be hydrogen distribution. 2 hydrogen from here will attach to these single bonds. So it means here you're expecting to get CH2. We are left with 2 more hydrogens. The 2 more hydrogens will react with this nitrogen to give us NH2. So we expect to get NH2 here. Okay, so all in all, the carbon of the functional group at the end of this reduction reaction is going to change to CH2, and on that carbon, NH2. And this NH2 is an amine compound, and that's why you can see the product formed, CH3, CH2. Look at it, unaffected, because the 2 carbon here are not the carbons of the functional group. This is the only carbon being affected because this is the functional group carbon. As it is being attacked, as explained here, 2 of the hydrogen will attach itself to this carbon. You have CH2, then the remaining single bond will now be attached to this NH2 because 2 remaining hydrogen here will react with this nitrogen. And what is the name of this compound? This compound is a primary amine. A primary amine. And like you're going to learn under amine, okay, the general nomenclature of primary amine, for simple primary amine, we generally call them alkylamine. Alkylamine. Now, what's the alky here? CH3, CH2, CH2. This is propyl, and therefore we call this compound propylamine. Propylamine. I'm going to write it somewhere here. Okay. There are some cases in primary amine that we call them as aminoalkane. When we discuss amine and its compound, we're going to learn that. So this is how the chemical reaction of nitrite occurs.